Hello everyone, this is part of a problem-solving series that would help you prepare for math competitions such as the AMC 10 and 12, the AIME, and other contests and tournaments in the advanced middle school and high school level. In this session, we will be solving a combinatorics problem from the ARML competition. Here's a view of this problem. The 6 sides of a convex hexagon are colored red. So let's go ahead and just draw a convex hexagon. Something like that, I guess. It's not necessarily regular, obviously, and our sides are our vertices are A1, A2, A3, A4, A5, and A6, and those sides are already colored red. So that's good. So let's continue. Each of the diagonals of the hexagon is colored either red or blue, and we are to compute the number of colorings such that every triangle has at least one red side. So let's try to first figure out how we can obtain triangles using the diagonals or the sides of our hexagon. So one way would be to use one of the 3 main diagonals, but then it gets us thinking, because the only way to properly construct a triangle using one of the main diagonals is to actually use the sides of our hexagon. And to prove that, so let's assume that we take this one here, this diagonal, main diagonal here, which connects 2 opposing vertices, and then we have 2 cases. Without loss of generality, we can choose either one of the sides. Let's assume we are choosing the right side here, and we have 2 options. If we continue from the edge here, then we are done, so that we are creating a triangle using that edge. So we do not want to use this edge. So as a result, in order to create a non-degenerate triangle, I have to connect to this point, and then boom, this time I have to use this edge here and again. So therefore, anytime I'm using one of the main diagonals, I'm automatically using one of the side lengths, and as a result, the coloring of the main diagonal here is irrelevant, because I have 3 of those main diagonals. Each one can be colored either red or blue, it doesn't matter. Regardless, we always excuse me, we always get our triangle have at least one side which is red, namely the one of the edges of our hexagon. So we have 3 main diagonals, and for those 3 main diagonals, each one can be colored in 2 different ways for a total of 8 ways. Now let's focus on the other diagonals of our hexagon. Now what is interesting in this case is we might have 2 different types of configuration where we are not making use of the edges of our original hexagon at all. So this is one of those triangles, and the other one is obviously this one. Let's focus on this straight line triangle here, namely triangle A1, A3, A5. That was a 3 here. So for this triangle, we can color each of the edges in 2 different ways. So for a total of 8 different ways we can color this triangle. However, one of these colorings might be all blue sides, and we do not want that case. We want at least one side showing up as red. So as a result, there are 7 different ways to color this solid this straight line triangle, and similarly 7 different ways to color this dashed triangle A2, A4, A6 as well. So 7 times 7 would give us 49 different ways to color those two triangles properly. And now finally, by using the product rule, we can multiply these two quantities to find out that 8 times 49 is actually equal to 392. So we claim that there are 392 different ways to color this hexagon diagonal so that every triangle has at least one red side, and that completes our solution. Hope to see you in our next session.